So in the last class we drew some pictorial diagrams and gave some set theoretic definitions, but we are yet to establish a correspondence between these two, right? Okay, so let's try to see how we manage to do that. So what was the last theorem that was discussed in the last class? This was done, I think. We are about to start from there, na?
Here.
This is the theorem. Yes. So just a minute. Hmm. So the statement is like this, that x pi is a map from x to x tilde, which is the natural canonical map. F is a map from x tilde to z, and from x to z we define f compose pi naturally. Now f is continuous if and only if f compose pi is continuous. So one part is obvious, right? Because x tilde is given the quotient topology. So if pi is continuous and f is continuous, then of course f compose pi is continuous. But what about the opposite? And we will see, while proving the opposite part, the converse part, we will need the fact that pi is a quotient map. It's not always true that if f compose g is continuous, then if and g is continuous, f may not always be continuous. But since pi is a quotient map, we will see that this actually holds. Okay, so suppose u is open. Don't forget the diagram, okay? So this is x, x tilde, z, f, pi, f compose pi. I think I forgot to send you the the notes, right?
Yeah.
Hmm. So hmm. So basically, suppose u is open in z, we will show pi inverse u is open in x. So if compose pi inverse u is open in x, this is open in x, And you know, since pi is the quotient topology, if pi inverse of some set is open in X, then by definition that set is open in X tilde. Okay. Thus F is a quotient map. Okay. Remember these theorems very carefully. You will need them at every stage. And this theorem, sometimes a version of this will be called the fundamental theorem of quotient topology. Okay. We will see, we will reach there, don't worry. So, before we reach there, should we state it first? Okay, we will state it a bit later. Just a minute. So here is a new setup. So suppose if X to Y is a surjective map, suppose that there is a topology on Y is the largest for which F is continuous. Okay. So clearly this is the identification map from X to Y. We consider the partition F inverse Y for each Y belongs to capital Y. Okay, so this is called the fibers with respect to fibers of small y with respect to F. Clear? The equivalence relation induced by this, then this is a homeomorphism. Okay, wait a minute, we see this thing in a bit detail. Just a minute, because this is probably the most important theorem in this chapter. Okay, so what they are doing is, see, so let's see pictorially what they are doing. So suppose this is your X, okay, and this is your Y, okay. Maybe I should write Y like this, okay. So basically what they are doing is that you pick up this line, okay. So they are sending this whole line to this, okay, this point, okay. Then they are sending this whole line to this point, okay. They are sending this whole line to this point, okay. So if this is y1 and this is say line 1, or maybe line with respect to y1, that's you should write. This is suppose y3, this is line with respect to y3. So the whole line is mapped to y1, a single point, right? So what is F inverse y1? That is L of y1, right? So always this set f inverse y is said is called the fiber of y with respect to f. Okay. Now see, observe that this is a partition on x. Okay. This is indeed an equivalence relation, because suppose you see, so what is the equivalence relation? X, x1, x2. So the equivalence relation is like this. So x1 is related to x2 if x1 comma x2 belongs to f inverse y for some y. Okay. So check that this is an equivalence relation. Whatever I am leaving you for to check, I expect you to really check it. Don't just trust me. So this is an equivalence relation. So it will induce some equivalence classes, some partition of x. So thus we get x tilde. Okay. So automatically you get a map f tilde from y. How? So see, how is f tilde defined? So f tilde is defined from, in a very natural way, from class x to fx. Tell me, have you seen it somewhere? Have you seen this type of scene somewhere?
Group theory,
Very
isomorphism
good.
theorem.
The group isomorphism theorem was exactly like this, right? So it was like G here and H here, and we used a map from G mod car phi to do this, right? So the idea is exactly similar. So you see it is well defined. So first of all, you are defining a map from a set of equivalence classes. So the most important thing is to check the well definedness. You can always define a map, but you will have to check the well definedness. So you see, if class x1 is class x2, it means x1 is related to x2, which means x1 is and x2 both are in same fiber, which means fx1 and fx2 equals to y, which is f tilde x1 and f tilde x2. Hence the map is well defined. Okay. Now we move on to the next theorem. Okay, so corollary. We already have this, right? We already saw this, right? So this is already we have seen. Combining this, we are going to define the universal theorem of quotient topology. Okay. So once we have all this, we can define the corollary, which is universal theorem of quotient topology. What is that? Let if let x to yb x and y be two topological spaces. Then and if from x to y topological spaces tilde an equivalence relation on x and if x to y a continuous. Sometimes we write map, it means continuous functions in our language. Then
আচ্ছা এই টিল্ডাটা যে ইনডিউসড বাই এফ এটা কি লেখা উচিত?
not yet. That's not the assumption. I mean, not yet.
ওকে,
If has the property that it is constant on the fibers, constant on the equivalence class with respect to tilde. That is fx equals to fx1 equals to fx2 if x1 is related to x2. Then if induces if tilde from x tilde to y such that if tilde is continuous. Okay. Just a minute, have I said it correct? I think it is correct. Just a minute, let me check the statement. So this map is unique first. So let me see. So I mean this is correct now because the map is to be well defined, so it has to be continuous on yes, it has to be continuous on the equivalence classes. Yes, it is true. It is true. Okay. So you see, a quotient topology sometimes it is characterized by these two maps, right? Because y is an arbitrary space. f is an arbitrary function, but this pi and x tilde are fixed. Okay. So this is called the universal theorem of quotient topology, or maybe universal property of quotient topology. We will use it a lot. Now let's move on to our theorem. That again, have a look at this statement first, the setup. So f is a surjective map from x to y. Okay. The partition on x is given by the fibers with respect to f. Okay. So in this case f is surjective. So f tilde is like this, f tilde well defined. Then we will show that f tilde is indeed a homeomorphism. So this is not a very difficult proof. Just a minute. This is the most important theorem I feel in this chapter. I mean in this section. Because this is the theorem which will actually help us to establish the connection between the pictorials diagram that we drew first and the set theoretic things we have been defined since we have been defining since. So okay, so this is okay. So I give you 5 minutes to look at this proof. Please look at this proof, then we will move on to the exercises. Not exactly exercises, but to those connection that I am telling you. Okay. Is there a doubt? So is there a doubt? Hello? Is there a doubt?
নো।
সবাই বেরিয়ে গেল কেন বলতো?
আছি।
না মানে হঠাৎ করে দেখলাম কেটে বললো তো।
দুজন গেছে, অর্পণ আর তিস্তা।
হুম। এই গ্রুপে ঈশান টিশানেরা নেই? দাঁড়া তো এক সেকেন্ড। আচ্ছা ঈশান গ্রুপটায় আছে?
কোন গ্রুপ দাদা?
আমার মাথা পুরো খারাপ হয়ে গেছে, আমি কাকে কি
হ্যাঁ
বলছি কি
আছে, আছে,
বলেছি। ঈশান
আছে।
গ্রুপটায় আছে?
হুম, হুম।
কিন্তু এক্ষুনি অ্যাড করালাম আমি।
ফিডব্যাক গ্রুপ?
না না, এটা কোশ্চেন টোপোলজি গ্রুপ। ঈশান কি আগে ছিল ওখানে?
আছে তো দেখছি।
আমি এদের কালকে বলেছি ক্লাস করাবো, দিয়ে আমি জানাতে ভুলে গেছি। ওফ, মাথাটা পুরো গেছে আমার।
ওরা পোলে ভোট করেনি বলে আমি তো অ্যাড করিনি, আমি তো জানি
না
না।
না ঠিক আছে, সে আমি ওদের তারপরে বলেছিলাম যে আমি আর বলতে ভুলে গেছি। আরে হ্যাঁ, নিজে বলেছি এদেরকে ক্লাসে আসতে, এখন নিজেই এদের গ্রুপে অ্যাড করতে ভুলে গেছি, আমার মাথাগুলো খারাপ হয়ে গেছে। So there. Okay, suppose this is a straight line, okay, call it I. So if we join these two ends, what do we get? We get a circle, right? Right? So now see, the problem is, the problem here is pictorially it's a circle. It is a circle, but topologically, by that we mean x is I, okay, and x tilde has quotient topology. On the other hand, a circle is basically S1 subset of R2, right? So we have to show x tilde is homeomorphic to S1, right? You understand the problem? Pictorially it's a circle, but the topology on x tilde is the quotient topology. On the other hand, S1 is embedded in R2. On the face of it, they have no connection whatsoever, right?
মানে S1 এর আর2 কোনো কানেকশন নেই বলতে কি বলতে চাইছো?
No. On the face of it, there may not be any connection between x tilde and between I tilde and S1. See, pictorially you are seeing that there is I'm joining two ends and hence it's a circle. But what about the topology? Two sets can have different topologies, right?
হ্যাঁ,
What is this set? This is I tilde, right? This is not yet embedded in R2. This is not yet homeomorphic to S1. You understand the problem? So don't just think that by gluing the thing is done. Just because you are pictorially watching an object like a circle, it's a circle. No, it's not that way. I mean, how do you even know that this circle may have a cofinite topology? S1 has the subspace topology of R2, right? Subspace topology, right? And I tilde has quotient topology of I. These may not be related even. So there comes the theorem, this theorem. So if you can find an f such that, from I to the circle, such that the inverse of f, the fibers of f will create the circle, create that particular equivalence class, then we are done, right? So from the theorem above, it is enough to find a surjective continuous what was that? Was F a quotient map there? Surjective continuous map if from I to S1 such that okay, but before that we will have to do something. Just a minute. So keep that question in mind. First, let's talk about this theorem. See, this is an easy theorem, right? So if x to y is a continuous surjective map and x is compact, y is Hausdorff, then F is an identification map. Okay? Because you remember we showed that every closed map or every open map is an identification map, right? So we will show that F is a closed map. So you see A is closed in X. Okay, since X is compact, A is also compact in X. Closed subspace of a compact space is compact. If A is compact in Y because F is continuous. So Fs is closed in Y since Y is Hausdorff. So a compact set of a Hausdorff space is closed. Thus A is closed. Okay. So F is a closed map. Hence F is an identification map. Clear? Clear?
Yeah. Yes.
This is a very important theorem. Okay, I will send you the note anyway. Just let me write down this observation. So this is one observation, okay? Another is the one that we just used before about the continuity. This is one. If compose pi, the continuity of this. This is the homeomorphism. This is one of them. And this is so there was F to be was F a quotient map there? Surjective map. Pi is a quotient map. Was there another similar theorem? No, that's it. We will use the following. So first define. So for this, okay, this is an example. Okay. So first define what gluing means in terms of set theory. So first let's define gluing in terms of identification. Okay. So first let's see that above example. Okay. So when we say that you glue these two ends of I, what do we actually mean? We mean to define an equivalence relation on I such that 0 such that 0, 1 are in the same partition. So basically define by, so we are defining this on I. Okay, so what are the partitions? So the partition has the following sets. So you keep 0 and 1 in one inside a single set, then you take x such that x belongs to open 0, 1. Okay, so you see you are gluing 0 and 1, right? That's why they are in the same set, and there is no gluing done in this part. Okay, hence they are left alone, they are left undisturbed. Clear? Clear?
আচ্ছা এখানে মানে গ্লুইং হচ্ছে, ম্যাপটা লিখে দেওয়া উচিত না?
লিখবো তো বটে।
হুম।
So in general we say x1 and x2 belongs to x is glued together if there exists an equivalence relation, if an equivalence relation is defined on if an equivalence on x such that x1 related to x2. Okay, so in this case you can observe 0 is related to 1, so that is the definition of gluing. Clear? Clear? When we talk about gluing, we mean give an equivalence relation on the domain, I mean on the mother space X, so that the things you want to glue are in the same partition. Okay, now I, okay, 0, 1 to S2, define this map F. The map is T going to cos 2 pi T sin 2 pi T. Okay, so this is continuous because this is continuous in each component. Now see, the domain is compact, right? The codomain is Hausdorff, right? So F is closed. So F is a quotient map, right? Tell me, what are the fibers of F? So what is F inverse 1, 0? What is that? What is F inverse 1, 0? It is nothing but 0 and 1, right? Right?
Yeah.
And what is F inverse, say, P, for P belongs to S1 minus 1, 0? That is singleton. That is just singleton. Okay? Because you see, I mean, P is of the form what? So P is here, right? P is there. So P is of the form, say, cos 2 pi T1, comma, sine 2 pi T2, right? Okay, maybe I should write it more precisely. See that F is bijective, I mean to S1, okay, F is bijective on 0, 1 from 0, 1 to S1 minus 0. Is that clear? Is it clear that F is bijective in this domain? Because if you take F T1 equals to F T2, you get, I mean, you can also write it like e to the power 2 pi IET, okay? Thinking R2 like C. These are same, these are homeomorphic. So you get e to the power 2 pi IT1, e to the power 2 pi IT2, okay? So T1 minus T2 belongs to Z, right? But as you can see, T1 and T2, so T1 minus T2 mod is less than what? Is strictly less than 1 because they are both inside this. So T1 equals to T2. Okay. Thus we have F inverse P to be singleton if P is not 1, 0. So what have we obtained? What have we obtained? Thus we see that the fibers with respect to F are, what are the fibers with respect to F are? So one is F inverse 1, 0 and F inverse P. So these are all singleton, right? Because there is unique pre-image of P if P is not 0, 1, which is same as 0, 1 and X. X belongs to 0, 1. Right? Now let's move back to this theorem. Now this is clear? Now this is clear. Why X tilde is homeomorphic to Y? So Y is S1 in this case. By that theorem, you have X equals to I, X tilde, that is I tilde. You had S1, F, hence you have F tilde, which is an isomorphism. Clear? So now you have I tilde is homeomorphic to S1. Now the proof is complete. see if anything else is under. Okay, so in the last class, I think we defined a lot of things pictorially, right? Cylinders and all that. Now let's define them. Now let's define them. So if you remember how this is how the Mobius strip was created, right? This was the identification and we glued it, right? So by gluing you mean you have to put this point. Now we have defined gluing. What is gluing? So by gluing you mean you have to give a partition on I cross I so that this point and this point, this point and this point, I mean this and this are in the same partition, this and this are in the same partition, this and this are in the same partition, right? And in the interior it is bijective, right? That's that, because you are gluing the bound, the horizon, the vertical boundaries only. Now look at this. This is the gluing. Okay. Have a look at this gluing.
দাদা বলছিলাম জিমে আমি কোয়ালিফাই করেছি।
So now is that clear? That how to define a gluing? Tell me when you are done. So this is the gluing of Mobius strip, okay? Below is the moving of, below is the torus. Don't worry, I will send you the notes. Clear? The gluing of Mobius, the torus.
Yeah.
Okay. The space 1 is equivalent to torus Klein's body. So we can do this thing for torus as well. Let's do the same problem for torus because it is directly related to. So we have defined torus by gluing, right? So this is how we define torus, right? Like this. Okay. What was it? Arrow. And we had this was our torus, but this is just pictorially. Torus is by definition this. So this is one thing, and torus is also defined this way, S1 cross S1. Okay. So if this is X and this is X tilde, so you have two definitions of torus, right? One is from X, after this identification you get X tilde, another is S1 cross S1. Okay. We will show that they are homeomorphic. How? You take X to be I cross I. You take S1 cross S1 inside R2. Take F like this. You send X comma Y to e to the power 2 pi I X comma e to the power 2 pi I Y. Okay. And then you get I cross I tilde by this identification. The one by this identification. Okay. Now again, this is compact. This is Hausdorff, right? So F is a quotient map. The only thing left to check is that the fibers with respect to if matches the partition if agrees with the partition induced by this on I cross I, right? Then we are done. Basically, what do you have to show? There is an equivalence relation, right? But we will have to show that this is the same equivalence relation as this, right? So this is done here, okay? So I will send you the notes. This is done here. And you can check it yourself. Actually, you should check it yourself. I did everything myself. So if inverse 1 comma this is this, everything is done here. Okay, you can just copy this. This is Klein's bottle. So this is the gluing of Klein's bottle. Okay. So if you have little bit of time, yes we do, let's define the topological cone. Have a look at this. Have a look at this and see that this is the same thing that we defined in the first class. Okay, so let's define a cone. Okay, so we will define two things. One is called the geometric cone, another is called the topological cone. Okay, so normally we know that a cone is basically that looks like this, right? Right, a cone is something, but in this case we are seeing this cone as an identification space, which comes after this. From a cylinder you identify the whole upper boundary to a point. Okay, that's the idea. So we define two things, one is the topological cone, another is the geometric cone, and we will show that these two are isomorphic. Okay, so the cone construction. first you get a topological space, okay, and then you take I, you do X cross I and give product topology. So, and then you define some equivalence relation on that set, okay. Okay. So this is suppose your X, okay. This is your X cross I. Now you see the equivalence relation, how is it given? So you see the whole X cross 1, that is this region, okay, this region, I mean this whole upper circle or maybe the upper boundary, that the whole thing is in a single partition. So this whole first circle maybe or the first boundary will be glued and everything else is a singleton, okay. So you are leaving the other points undisturbed, hence you get this structure, okay, clear? So this is, so from X to X cross I we define a geometric cone on X, okay, I mean a topological cone on X. And what is a geometric cone? A geometric cone is this. So here you take X inside Rn, okay, a compact set, okay, a compact set inside Rn you take, and then you define this. This is just a figure, huh? Not an equivalence relation or something like that. With respect to X, you are just defining a set, okay. So basically see what you are doing is that X is below, you have gone to one step, one dimension higher, you are seeing X now in Rn plus 1, then you are joining, then you are fixing a point V which is just 0, 0, 0, 1, then you are joining every line from X to V, and the whole set of lines along with the point V and along with the compact set X embedded in Rn plus 1, this whole thing is called the geometric cone, okay. So naturally you will have to show that if this X, this topological cone, this topological space X is a compact subset of Rn, then Gx is homeomorphic to Cx, right? You will have to show that geometric and topological definitions of cone agree for a compact subset of Rn, right? So we will probably see that and we can actually conclude today's class by that. But what I am looking for is the attaching maps. Joydipta has actually told me to teach you the attaching maps, but before that we will go to submit problems. So that the spaces are isomorphic, yeah, this is one of the problems. So RP2 will be defined in the next class. Identify all the points in a Mobius circle. What is that? Okay, attaching maps, this will be done in the next class, okay, very good. So let's define, give an isomorphism between the topological cone and the geometric cone. So again you take X as a subset of Rn which is compact, okay, and you take X cross I, right? From X cross I to topological cone Cx, the definition of Cx here is it, okay, okay. So I am defining a map F. So you remember the theorem that we have used twice for torus and for circle. This time X will be replaced by X cross I, okay. This time X will be replaced by X cross I. So you give x cross I tilde to make the topological cone. Let's give topological cone a notation. I mean, let's give it say tau x. No, it was gx, it is given, right? So gx and this is cx. Topological cone is given already, the notation cx. Okay, sorry. So this is cx. Okay, fine. The identification is this one. Okay, this is the identification. So we will try to find out f tilde. Okay, so just as before, we define f to be what? You look at these things, look at the partitions, and we will do exactly that. Okay, so you send x comma 1 to v for all x belongs to x, right? That is, the whole x cross 1 is getting mapped into v, and f of x comma t okay, leave it there. Just use this. This is the best way to define it. Just use this. Okay, the best way to define it, this relation. So you define f of x comma t to be tv plus 1 minus t into x. Okay, for x comma t belongs to x cross I. Just use this definition of geometric cone to define the map. Okay, clear? So you will see that f inverse of what should I say, v is nothing but x cross 1. Okay, which will be just, and check
এই ওপরেরটা জিএক্স হবে তো,
কোনটাই
এই এক্স ক্রস আই থেকে যেটা হয়ে
so check that this is, and f is bijective on x cross closed 0 open 1. You check these two things, right? Again, this is in Rn plus 1. Okay, so this is Hausdorff. This x is compact, I is compact, so this is compact. So again you have f a closed map, again a quotient map, and the whole thing is same. Okay, so there you will be able to show that this f map, the fibers generated by f are basically the partitions that you need for x cross I to reach cx. Okay, that's it for today. I have another class starting from 10 p.m. today. Okay, that's it.